Today we're going to introduce the concept of differential equations and how to solve them through the method of separation of variables. Here we can see the definition that Wolfram Alpha gives for a differential equation. A differential equation is an equation involving a function and its derivatives. It can be referred to as an ordinary differential equation or a partial differential equation depending on whether or not partial derivatives are involved. For us, in the IB syllabus, we are only going to deal with ordinary differential equations. And the differential equation can be seen, for example, when you take the derivative of a function with respect to x, and you have something equals to that derivative on the right hand side. So for example, this is a very simple differential equation. And the method of separation of variables will help you to solve this differential equation. Now, we have used this method before, we just didn't give a name to it. And you have dealt with differential equations of this kind before, we just didn't mention them as such. What is the idea of solving a differential equation? When you want to solve a differential equation, what you're actually finding is what function satisfies that relationship between the derivatives and the function. So the goal of solving a differential equation is finding the function. In general, some of the differential equations that we're going to be working with have this form. So you have the first derivative to one side, and then you have a function of x and y on the right hand side. To use separation of variables, you need to make sure to set up your differential equation in such a way that the function f of xy can be expressed as the product of two different functions. One function that is a function of x and one other function that is a function of y. So that when you do replace the function in that way, g of x times h of y, you can move around all the variables, and the idea will be to put the variables that have the y on the left hand side, so 1 over h of y dy, and then the variables that have x on the right hand side, g of x dx. When you reach this step in the process, you are going to just integrate. So you're going to integrate 1 over h of y dy equals the integral of g of x dx. Now the idea is that these differential equations are going to be simple enough that by finding this integral, you will be able to solve later on this equation for y and find an expression for the function y in terms of x. Let's see this process and work with our first example. Show that the solution to the differential equation dy over dx is equal to xy minus x can be written in the form y equals 1 plus a times e to the power of x squared over 2 if y is bigger than 1. So the first thing we have to do, like we said before, is to make sure that the function that we have in the right hand side can be expressed as the product of two functions, one that is a function of x and one that is a function of y. So dy over dx, if I factorize the x, I'm going to get x common factor of y minus 1, and then I have two functions. The first function is simply x, only a function of x, and the second function is y minus 1, which is only a function of y. At this point, we can proceed to do the separation of variables. How do we do that? We need to move everything that has y to one side and everything that has x to the other side. So we're going to move everything that has y to the left. So we're going to divide by y minus 1. And we're going to move the dx to the right. So we're going to multiply by dx on the right hand side. That is 1 over y minus 1 dy equals x dx. At this point, the variables have been separated. I can proceed to integrate on both sides. So I get the integral, indefinite integrals on both sides. The integral of 1 over y minus 1 is ln of absolute value of y minus 1. And the integral of x is x squared over 2. And because these are indefinite integrals, I need to add a plus c. Now, since we know that y is going to be bigger than 1, because that is a condition for the solution that we're trying to find, then we know that the argument of the absolute value is going to be positive. So we can write, instead of absolute value of y minus 1, we can just switch this to a regular bracket, y minus 1. And what we're going to do next is we're going to put everything as a power of e. So we're going to do e to the power of ln x minus 1, e to the power of x squared over 2 plus c. And when we do this, e and ln, the natural logarithm, they are inverse functions. So what we get in the left hand side is y minus 1. And to the right hand side, we can just separate this into two exponentials, x squared over 2 times e power c. Now I'm going to define the variable a as e power c. And, well, that's not a variable, that's a constant. So I'm going to just give it a different name, a, and that's going to be a e to the power of x squared over 2. And that takes care of this part of the solution. Now we have this minus 1 in the left hand side that I need to move to the right hand side to complete the final answer, 1 plus a e to the power of x squared over 2. So we have shown that the solution can be expressed in the form that was required by the question. Let me show you a second example. Solve the differential equation cosine squared of x times dy over dx equals e to the power of minus 2y. Now, it's not always necessary for you to move everything to the right hand side first. You can always start separating the variables right away. So in this case, I'm just going to move these two items to the right hand side at once and then bring this expression, e to the power of minus 2y, to the left hand side also. So this would be e to the power of 2y dy equals 1 over cosine squared of x times dx. So that my variables are now separated. And I can do the next step, which would be to integrate. So I'm going to integrate both sides, and I'm going to rewrite the right hand side as secant squared. So secant squared of x dx. The integral in the left hand side is going to be equal to 1 over 2 e to the power of 2y, and the integral in the right hand side is going to be tangent. So tangent x, and don't forget the plus c because these are indefinite integrals. Now, in order to find the value of the constant of integration, we need to use this extra information that we were given. So when x is pi by 4, y is equal to a half. So before I solve for y, I'm just going to substitute those values in order to find c. So 1 half e to the power of 2 times 1 half is equal to tangent of pi by 4 plus c. Now we know that tangent of pi by 4 is 1, and e to the power of 2 over 2 is just e, so it's 1 half of e. That means the value of c is going to be 1 half e minus 1. Now I'm going to substitute that into my previous expression. So 1 half e to the power of 2y equals tangent x plus 1 half e minus 1. And now I'm going to solve for y. So first I'm going to multiply everything by 2. E to the power of 2y is equal to 2 tangent x plus e minus 2. And now I'm going to do natural logarithm on both sides. So ln e power 2y is equal to ln 2 tangent plus e minus 2. Now natural logarithm and the exponential are inverse functions, so they would mutually cancel, and we get just 2y equals the same thing that we have above. And to answer the question, I just need to finish by dividing by 2. So y will be equal to 1/2 of ln of 2 tangent x plus e minus 2. And this would be the final answer. Now to finish, I am writing here two different differential equations for you to try. They are very similar to the ones that I showed you in this video. Please try this as homework.